Another interesting way to graph polar equations would be to maybe look at the rectangular coordinate system version of the graph to use it to get a table of values basically. So for example, if I wanted to graph the equation r equals, let me change my thickness here, r equals cosine of 2 theta. One thing you could do is look at the rectangular system graph first. Rectangular just means you basically have an x and a y axis. So in this case, here's my y-axis, here's my x-axis, but instead of calling them x and y, I'll call this r and I'll call this theta. Okay? And so if you remember the cosine function, it looks, it looks something like this, and it repeats forever. Okay? And in fact, the period from here to here was 2 pi for the cosine function, but we're not graphing cosine, we're graphing cosine of 2 times an angle, so this 2 is a horizontal shrink by 2. So that means that our period here is not 2 pi, but pi instead. Okay? So that means that this is pi over 2, this would be 3 pi over 2, this would be 2 pi, etc. We could even name these points here 3 pi over 4, pi over 4, 5 pi over 4, 7 pi over 4, and finally here would be 9 pi over 4, and we could keep naming points if we wanted to. My point is, now you can clearly see what happens to r as theta gets bigger and bigger. So let's graph this on the polar plane now. So what you can see, let's look at all these nice points where r is 0 now, right? Because our r-axis is 0 at those red points. So when theta is pi over 4, that's right here, r is 0. So at all those pi over 4s, r is 0. So we're always going to come back to that point 0. Alright, now let's look at maybe where all the points are 1, where r is 1. So r is 1 away from the origin at 0, pi, and 2 pi. So at 0 we're at 1 away. At pi, which is over here, we're 1 away. At 2 pi we're 1 away, so we're back over there. Let's look where we're negative 1 from the origin. So that's at pi over 2, 3 pi over 2. This would be 5 pi over 2. So at pi over 2 we're negative 1 away. So pi over 2 is right here. We're negative 1 away. That's down here. 3 pi over 2 is down here. We're negative 1 away. So that's up here. 5 pi over 2 is just pi over 2, so that repeats now. Now let's start looking at the pattern in between. So when theta goes from 0 to pi over 4, r decreases from 1 up here down to 0. So that means on our graph, when theta goes from 0 to pi over 4, let me draw in the pi over 4 again. That's right here. When theta goes from 0 to pi over 4, r decreases from 1 down to 0. What does that mean here? That means r decreases from 1 down to 0. And you get that. Then if we look at the next region from pi over 4 to pi over 2, r keeps decreasing to negative 1. So in our graph over here, pi over 4 to pi over 2 is right here. R goes from 0 down to negative 1. Negative 1 right here would be, it circles around and comes down to negative 1 at pi over 2, right? Because at pi over 2 it's negative 1, so it has to come down here. And then we keep following this sort of pattern from pi over 2 to 3 pi over 4. That's this region in our graph, pi over 2 to 3 pi over 4. It goes back from negative 1 to 0. So from negative 1 is down here, back to 0 does something like that. Look at the next region from 3 pi over 4 to pi. In our graph, 3 pi over 4 to pi is right here. It goes from 0 back up to 1. So it's at 0 now. It goes at pi, it goes back to 1, so it circles back around like this. And if you keep following it all the way around, you'll see that it does something like this. And so you end up with, you keep going, you'll end up with what's called a four-leaved rose. So it's another interesting way to graph polar equations without actually plotting too many points. Here you get to understand the pattern as to what happens, and you can actually see it by looking at the rectangular version of the coordinate system.